Here's a proposition for you. So today I'm going to be talking about the theory of dimension. So basically I'm going to share with you about 10 or so propositions or theorems which are foundational to the core logic in this course. I'll prove a few of them. Let me start out with a basic one. So proposition 6.6.1. It's on page 139. My notes, current edition. So here's the deal. Let B be a finite dimensional vector space, and suppose beta is any basis of B. Let B be vector space with basis beta equal to B1, B2, Bn. Then, first point, beta union any vector is linearly dependent. And point number 2, for any 1 less than or equal to k less than or equal to n, the set B with one of these guys, a piece of k, or the piece of k removed, does not span B. Okay. All right. Now, what was the basis? We defined that, yeah.
It spans B and it's linearly independent.
Right. So two things, right? Like you just said, the span beta is equal to B, and also beta is linearly independent. You have those two things. That's what we mean when we say basis. It's also an ordered set. Right?
Is that an N or a K in the braces? The B minus?
Okay. Okay. I mean, it would also be true for n, but in particular, I'm thinking about just any. Basically, if you just remove anything from the list, remove any of those from the list. Just take one out. You don't get everything back. In other words, each thing in the basis is needed. Take even one thing out of the basis, you lose something from the span. You don't get all of the. Okay, so proof. How would we prove 1? Yeah.
V is an element of B, big B. So
Yes,
it's,
B is an element of
of the span. Yeah, of the
yeah,
span
you're
of
saying
beta.
B, which is big D, which is equal to the span beta, and then what?
So it's a linear combination of B1, B2.
Right. Oops. Messing with me. I don't usually use B sub I for vectors. It's kind of weird. Not like it. Oh, and that. What does that say?
That's I, isn't it? Okay. I
Yeah.
see right
So, hence, beta union with the singleton containing B has the linear dependence above. Okay. There you go. That proves 1. That is a linearly dependent set.
Or is that union B union B, or what is that? The notation, like we did hence B
B union the set just containing the vector B.
Okay.
No. Yes, Chris?
So is that saying that if you have a basis and you add a vector to it, that that vector has to be a linear combination of what's in the basis already, so it becomes linear dependent?
Right. If we're talking about a basis for the whole vector space. Now, if I take what you said and just twist its context just a little bit, if I have a subspace, all right, and I have a basis for a subspace, if I add a vector to that, it may or may not become a linearly dependent set. It might be linearly independent, but then it would span a bigger space than that subspace. That's one of the theorems we'll look at later today. Point 2, what we do?
Assume it does span.
Yeah, exactly. So suppose the span of beta minus, some one piece of k does span B. Right? Then what I would do is I would pick on piece of k, right? Piece of k is an element of B, right? Which implies that, there exists C1, C2, N minus 1, such that what? Basically, the sum over I not equal to k of C sub I and B sub I is equal to B sub k, right? I mean, the point is, if that set without B sub k spans all of B, that means that spanning set, the generating set B minus bk, it has to pick up bk, right? Which means that you can write bk as a linear combination of the other b's, but guess what? That means that yeah?
It means that it's in it and we're not doing it.
Now what is it, what does this say about the set beta? Is not what?
Linearly independent.
Yeah, it's not linearly independent. So that would say that there's linear dependence in the basis, which is a contradiction of what we're assuming at the outset, right? Because we're assuming basis beta, right? So one of the things that means this is linearly independent, if we do like you said, basically we're working by a contradiction, right? You're assuming the opposite. You're assuming that it does span B. In particular, that means it has to pick up B sub k. But if it picks up B sub k, that means that you can write B sub k with all these vectors, which is everything except for the kth one. And that says that there's a linear dependence in the set beta, which contradicts our earlier assumption that beta is a basis.
So basically, B sub k has to be like located somewhere in there for it to span B. Right?
Yeah, that is the takeaway message of this. In other words, like every single part of a basis is necessary. Yeah, they're all, every vector is a planned and wanted vector.
You can't just remove
No removing them. Unless you want to change the span. All right. This is actually a special case of theorems I prove later. I like to start with this one though, because this one is particularly easy to prove. And it's got all the major ideas in it. Spanning, linear independence, basis. Good place to start. Now what I'm about to prove next is significantly harder to prove. So here he goes. And I probably should call this a theorem. I'm going to call it theorem 6.6.2. Seems like it's more than a proposition to me. It is a proposition in my notes currently. Let V be a finite dimensional. Now, what that means for us, what do I mean finite dimensional? Here, this just meaning there exists a basis for V with the number of things in beta less than infinity, okay? So to say, at the moment, my transitional definition for finite dimensional is just this. Well, that's not a transitional definition. That is the usual definition. To say a vector space is finite dimensional means that there exists a basis with finitely many things. Okay. The thing that bothers me about saying that at this point a little bit is that I have not yet defined dimension. Okay? But, I mean, we can nevertheless give meaning to that phrase. I'm just saying that there is a basis with finitely many things, okay? So, if beta and gamma are bases for B, then the number of elements of beta is equal to the number of elements of gamma. You guys with me? So in other words, if it's finite dimensional and you have a basis, the number of things in the basis is uniquely, it's some unique number. You can't find a basis, one basis with 3 things in it and another basis with 4 things in it. That can't happen. Yeah?
Well, I was gonna ask, does that mean that if that says that they're the exact same thing, right?
Yeah. So let's prove it. Here's the proof. So let beta equal to, let's say, B1, B2, all the way on up to B sub n. And let gamma equal to, let's say, W1, W2, all the way out to W sub P. All right. What's our goal? What do we want to show?
Show that B1 equals W1, B2 equals W2.
N equals P.
That's greedy. I can't assume that they're the same. I want to show that n. I want to show that the number. So like this has number of things in beta is P, right? Oh, I'm an idiot. Duh. N. Yeah, the number of things in the basis gamma is P. So we wish to show n equals to P. All right? And we're assuming what about beta and gamma? Linearly independent with what? Span beta equal to B. Again, linearly independent with what? B, yeah, exactly. You're both linear independent spanning sets. All right. So what we do is the following. Say, okay, well, since W1, or let's say W, yeah, I'll start with W, let me just say WJ, get to the point here. So since WJ is an element of the span of beta, what's that mean? We can write the J element of the gamma basis as a linear combination of the V's, right? So I can write a sum, say I equals 1 to n, let's say C ij. I mean, I don't know, the index structure here, I'm not really worried about what I've written in my notes. I may be slightly different than what's there. We'll figure it out, okay? V sub what? V sub I. Right, that would be equal to W sub I. Yeah.
How can you write it as, or in terms of V? Like you
Well,
wrote.
the V's span all, the V's, the V sub 1 through n, V sub 1 through n spans vector space, right? W sub j is a vector in the vector space. So there has to be some linear combination of the V's which reaches that j to W. Yeah.
Where did the WJ come from? You said it was from the vector space?
I'm just picking on a particular thing in the basis for gamma. So it's defined here.
Okay, how do we know that it's part of beta, or the span of beta?
Because the span of beta is V. I mean, span beta equals V, so it's everything in the vector space.
Okay.
There was another question?
I was asking this question, like, how do we know that, like, we're like, it just seems like, well, I mean, like, the moment that we know that, like, the elements of the span there we have it, that's the proof, like, that they're the same.
Oh, this isn't the proof yet. We're not done yet.
Well, like,
We're showing it in sequel.
What did this say that, like, both beta and gamma are the same basis? Or-
They're both bases, we're assuming that. We were trying to show that the number of things in both is the same.
But, like, what does that make them the same basis though? Or are
That's what we're trying to prove.
No,
Not
but
that-
what I mean is, okay, like, can they be the same number basis but like have different values?
Yes, oh yes. Like last time, we saw R3 has a non-standard basis, like 1, 0, 0, 1, 1, 0, and 1, 1, 1. That's different than, say,
Okay, so how do we know
3,
that WJ is in each beta?
I don't know that WJ is in beta.
Or
That's
in
not
the span
true.
of beta, right?
It's in the span of beta though. Because the span of beta covers the whole vector space. That's what it's in.
Okay, I got it. Sorry.
You're fine. So, likewise, we can do the same thing for VJ, right? So like, or let's say for VI. For VI, there has to be, is an element of the span of gamma, right? So that means I can pick other coefficients, all right? And let's use a different letter. Let's say some, I don't know, K. K equals 1 to P, right? Let's say D, keeping with my, say K I, W K, that would be equal to VI. I can choose constants dKi to make this so, because VI is in the span of gamma. Right?
Sorry, yes.
I mean, I just changed the same thing we just argued through. So now just, you pick your favorite one. I think I'm going to plug the purple one into the red one and see what happens. Right? So together, this gives me the sum I equals 1 to n, Cij, sum k equals 1 to p of d k I. Let's see here. The what? Oh, I'm going to get w sub k. All right, I just substituted that for vi up here. And all of that's equal to w sub k, right? So I just substituted the purple expression.
Would you have substituted the red one in?
You could have, but I did this.
You would
I
have.
replaced this with all of that, right? Yeah.
So just to clarify, you can say that Wj belongs to the span of beta because they both span the vector space,
Exactly.
the same vector space.
Yep. The given vector space V. Correct. Now I can use properties of finite sum. Yes.
Now, why do you, I'm trying to think how to phrase my question. So for the bottom one, you use a W, which is an element of gamma. For the top one, you use V sub I, which is an element of the vector space. Could we reverse that and do, say that V sub J is an element of the span of gamma?
That's what I do. That's what I do here.
No, B sub J, not V sub J.
Oh, there's no B's.
Oh.
Yeah, I'm sorry.
Oh, wow, okay, that was.
So, going back to this
that was
one.
like 5 proofs ago.
That's okay. This one was V2. I could have done it. See, better.
Okay, that makes so much more sense. Oh.
Better pedagogy would have been to use V1 through Vn back here, right? I didn't. Okay, so then we can clean this up, right? Properties of finite sums. You can write this instead as the sum I equals 1 to n, sum k equals 1 to p of d k I c I j. Let's see here. Oh, and I can flip the order of the sums too, right? We proved that back in chapter 1. I can say k equals 1 to p. I do actually have to flip the order of the summations here. I equals 1, y equals 1 to n. And then I got this stuff, and w's of k is equal to w's of j. So far, I have not yet used the linear independence of the bases. All I used was the fact that they were spanning sets so far. Now is the critical moment I must use linear independence. Look at this. On both sides we have w's, right? The set of the vector, the set, gamma is a linearly independent set. So that means I can what?
You can say, well, that can't be a constant. Like, I mean, you can't have wk multiplied by a constant equals wj, because that would imply that.
That is true. I want to be greedier than that, though. I want to use proper, yeah.
This set's a linear combination of other, wj is a linear combination of other vectors in gamma, so it's linear
You
dependent.
guys are still describing to me why that has to
So
work like
that
that.
constant has to be 0? Or
Yes, except, when is a constant not 0?
when it's not 0?
Yes, the constant is not 0 when it's not 0. As usual, I cannot argue with Dana's logic.
Except when one of those
Stop throwing your voice. We're doing this earlier this semester. Oh, wait a minute. That was very much a quintessential Chris comment.
Yeah.
Wait a minute, who said that?
That was me.
I'm very confused now. Look, guys, so tell me, there's no offense here if k is equal to j, right? If k is equal to j, then yeah, wj is equal to wj, but then this sum has to be 1. So the sum is either 0 or it's 1. I'm equating coefficients. Okay, that's what I was fishing for, right? We had that equating coefficients property, right? So equating coefficients. It tells me what? It tells me that the sum I equals 1 to n of b, k, I, c, I, j is equal to Kronecker delta kj. And that Kronecker delta kj is either 1 if k is equal to j, and it's 0 if k is not equal to j. But by almost the same argument, what else do I have? I have the sum, let's say, k equals 1 to p, well, not k, whatever index you want, L equals 1 to p of c. I guess I should put a, oh, curses. Here, K and J, what are K and J are what do they run over? Where's J coming from? J is coming from an index of gamma, right? And J is also an index of gamma. So here are K and J, 1 less than or equal to K comma J, less than or equal to 1. P, right? So I'm having trouble notationally seeing past something. I guess I need other letters. Let's say, I mean, you can do the same thing with C and D, like flipped around. So let's say C, I definitely want an L here and a D spelled there. I can't decide what to put here and here. If you don't mind, I'm going to put a Pac-Man and a ghost. And that will be Kronecker delta Pac-Man ghost. But same argument. Your Pac-Man and Ghost are between what?
They're gonna use some
Now, here the roles of beta and gamma are flipped around.
It's 1 and n.
1 and n, right? All right. Okay, so let's get on with it here. As a matrix equation, what this says is the following. This says that C times D is equal to I sub n. All right. This one over here says that D times C is equal to I sub P. The Kronecker delta is the component of the identity matrix, right? These are the components of the identity matrix. Now you guys, thankfully, that'd be nice and all, but that would be kind of like the end of it. But you guys did homework, right? And in your homework, you've shown something. So from your homework, and it's actually not that hard to prove. I wanted to give you guys some of the joy. The trace of C times D is equal to the trace of D times C. Did I say C times D? I can't remember what I said. Anyway, the point is you can flip the order. These matrices are multipliable in both ways. Well, anyway, to calculate the trace, I think you need a square matrix. At least as I usually talk about trace, you need a square matrix. Now, so on the one hand, we've got the trace of, let's see, C times D was I sub n. And on the other side, we've got the trace of I sub t. But what is the trace? Well, the trace says you take a square matrix and you add the diagonals. So like,
that means that they,
for those of you who have not done the homework yet, for example, the trace of 1, 2, 3, 4 would be equal to 1 plus 4. Yeah.
So it would be just 1 times n equals 1 times p.
Right. Or
And
I will take your 1 times n and replace with n.
Yeah.
But yes.
Well, n equals p, which means they have the same number of, that's what you were,
Indeed. We have now shown that the number of things in both bases is in fact the same.
complex number.
Dimension theory in any part of math is complicated. Even in linear algebra, dimension theory is a little bit hard to get your paws around. You notice that this is significantly more difficult than other terms we've done in here, I think, personally. But hey, now that we've done it, all kinds of fun facts will flow from this. In particular, we have now earned the right to define dimension. Woo. So what's the definition of dimension?
Dr. Cook,
Yeah.
how does equating the traces imply that?
Because if you have a trace of matrix with 1, 1, 1, and there are n of these, you get 1 plus 1 plus 1 plus 1 n times, right? Which is what?
And that's one.
It's n.
N. You know this.
But like you could use different numbers to get the same trait.
It's an identity matrix.
I mean, do other matrices have trace n? Do other matrices have trace p? Absolutely. I don't care about those other matrices. I care about the identity matrix, which is connected to connecting the different bases. So,
Oh, it's because it's the identity matrix.
oh yes, yes, the fact that, and that, again, was a combination of the fact that they're both spanning sets, as well as the fact that both of these sets are linearly independent, which ultimately allowed me to equate coefficients. Now, so here's the definition. if beta is a linearly independent set with the span of beta equals to v, then the number of vectors in beta is called the dimension of the vector space V. Well, provided the number of vectors in beta is less than infinity, okay. If there is not a finite basis, then we say that the vector space is infinite dimensional. Okay. Are there infinite dimensional vector spaces? Yes. Lots of them. You've been working with them for some time. Function spaces, for example. Polynomials. The reals are one-dimensional. Yep.
So why
Now,
does,
although the reals is a vector space over the rationals is infinite dimensional. What that means? Yes.
so why doesn't it work if there are infinite dimensions? Or why cannot grammar?
It goes back to this question. What's the largest number?
6.
I take 6 plus 1. My number's larger. Haha.
Infinity.
I give you infinity plus 1, which is larger. Haha, you lose.
Infinity plus one is
I mean, the trouble with infinity is, arithmetic breaks down a little bit. So if we want to do things with counting, we need finite numbers. Or we need transfinite arithmetic or something, which is something most of us are not.
So does it extend point to coordinates or just infinite coordinates? Or infinite parts?
Are there coordinates with respect to infinite bases? Yes.
Well,
But not that we talk about this course.
I'm.
I mean, what can be said about infinite dimensional vector spaces? Some things can be said. What of those things will we say? We will say some of those things. Can we say all of the things that can be said? No, I mean, I won't even say all the things that can be said for finite dimensional vector spaces. So I am cautious about infinite dimensional vector spaces, okay? Basically, the tool you need for infinite dimensional vector spaces to say things, a lot of times is analysis. Analysis brings quantitative things into, things.
Is there a course that goes into it?
Here? No. I don't think so. All right, let me get on with it here. Actually, at this point,
I'm just curious.
you have driven me to use the projector. So, you have projected me to the projector.
You were interested.
I mean, questions are good, but I must share with you these theorems today, so in the interest of me not writing like a banshee for the remaining 15 minutes.
Banshee's right.
What's that?
Said do Banshee's right.
I would imagine Banshee's good, right?
I don't know, I really never met one, so I guess what's your opinion on banshees writing? After
I'm just wondering what a banshee is.
What is
I've wondered
it?
that.
What
Aren't they the screaming ladies trying to catch the leprechauns?
Screaming
I know they
lady?
scream.
No?
That's about all I know about it.
They're dead women just scream.
Any mythical studies?
I don't know about the leprechauns.
They're dead.
They can mean a
I wouldn't
variety
put
of
it past
things,
them.
like, there's
What?
a lot of.
I wouldn't put it past them.
Where do we
Don't
go?
be too
I don't think that's part of the metaphysical qualities of banshee dum.
This is a silly place.
Wait, Mike. Were you being serious about that?
Yeah.
Seriously, are?
We should have a math problem about Banshees.
We have to walk up there. I like that.
All right, guys, the proofs I'm about to skip are actually easier than the ones I just showed you. So, and in some sense or another are in tune with the one we did carefully at the start of class here, okay? So, and well, I do write notes for you guys for a reason. Now, the one thing I will say is my proofs are not, the propositions in this section, I don't know if they're logically minimal, all right? So I think it's true that what I've told you in these notes is true, right? Could it be said with less words and get to the point with a smaller number of theorems? Yeah, probably. Some of these, I've gathered these theorems from a variety of sources, and I think, like I said, there may be some logical redundancy here, but probably doesn't hurt to hear something more than once either, does it? So. Here's proposition 6.6.5. You got a vector space of dimension n. Now we know what that means. It means you have a basis of n vectors. All right? Hey, what's the dimension of Rn?
N.
Yay! Because how many standard basis elements are there?
N.
N. So any other non-standard basis must also have
N.
n. Yes, you got it. Okay, so what's the dimension of n by n matrices? It's m times n, because there's exactly that many of those EIJs. Like so the matrix with a 1 in one spot and 0 elsewhere. There's as many of those as there are components in a matrix. There's as many components as the rows times the columns. So that's why the dimension of m by n matrices is m times n. These are really, really nice theorems. If you know the vector space, if you know your vector space has dimension n, that has to be a given, okay? Otherwise, you can't use the theorem. But if you know, then a set with more than n vectors, linearly dependent. All you gotta do is count. On the other hand, if you have a set with less than n vectors, you don't get the whole space. It can't be a spanning set. Yeah.
This is where S is a subset of E, right?
Of course. Yeah, otherwise it wouldn't make sense.
What happens to equal? What if it has three vectors?
Hmm?
What if it just has x vectors? You said more.
It may or may not. Depends on whether the set is linearly independent.
Yeah, fair enough.
That seems like it should be a theorem.
That's a theorem.
Now, the proof that I'm just skipping over here, it uses, basically what that proof is I take those propositions, I change them to statements about coordinate vectors. I then use the reduced echelon form on coordinate vectors to extrapolate the essential features of dependence or spanning, whatever it is, and then I rip that back to the coordinate vectors again and lift it back up to space. So like the proof that I just skipped over, essentially it's stealing from matrix theory. It's not a very good, I would say, linear algebraic proof. Yeah. Suppose V is vector space and dimension equals to n. Suppose that W is a subspace of V. Then there exists a basis for W, and the dimension of W is less than or equal to n. Can you flip the lights on here? Let me show you an example of this. So, how about this? Look at n by n matrices. For V. So set V equals to Rn by n. And I'm going to tell you guys, if I take W to be, let's say, A in Rn by n, such that what? How about this? A transpose equals to A. Is this a subspace? Prove or disprove? Let's prove it. How would we prove that's a subspace?
So it's closed under addition.
Right, and it's non-empty, right? So I'll be lazy, do the non-empty part first. How about this? 0 transpose equals to 0, right? Hey, so the 0 matrix satisfies the needed criteria to be in W. So the W club is not empty. Yeah, W is, some people find it useful to think of subspaces as like a club you're trying to get into. So suppose two of your friends, A and B, are in the club. And, I don't know what it means to add friends. Let's not take this analogy too far. Okay. So suppose A and B are in W. And, yes, I definitely don't want to explain that. All right, and C be an element of the reals. How about this? A or CA plus B, take the transpose of that, what do you get? Well, properties of transpose, so you can pull scalars out, and it distributes across addition. Property of transpose, right? But A and B are in W, right? That means that they're symmetric matrices, right? I'm claiming that the set of symmetric matrices is a subspace. For those of you who are keeping score. This is CA plus B because A transpose is equal to A and B transpose is equal to B, right? By assumption here. Hence what? CA plus B is an element of W. What's that thing Soprano says?
Falls right out.
And it falls right out. By what? Subspace theorem. W is a subspace of N by N matrices, right? Yes, sir.
So just because A transpose equals A, that means that B transpose equals B?
We're assuming that. As soon as I say that A and B are in W, what does that mean?
That they're N by N.
Yes, and what's the condition? What's the criteria which makes W what it is? Right here we defined it, okay. So it's N by N matrices such that,
The transpose equals.
so as soon as I say A and B are in W, I'm automatically assuming that A transpose is A and B transpose is B. That's part and parcel of what it means to be in W. Okay, well, this is not really today's material. My point to you is, this is a subspace, right? Now, if you ask me what's the spanning set for the symmetric matrices, I don't think it's altogether obvious, is it? I mean, I happen to know what it is, but I like these things. I've played with them before. It actually would take you a couple minutes of calculation to actually find the spanning set. And it might take you a couple more minutes to calculate the dimension for arbitrary n. I can tell you for 2 by 2 matrices, the dimension is 2, 3. For 3 by 3 matrices, the dimension is 6. For 4 by 4 matrices, the dimension of W is 9, I think. To actually figure out those dimensions, I'd have to do counting. But it's easy enough to see from this theorem, that the dimension of V is what, in this case? It's n squared. N by N matrices have dimension n squared, right? So I know that the dimension of W for any choice of n has to be less than n squared. Yeah?
Can you have negative dimensions?
No,
Okay.
not here. There's such a thing as fractional dimension, but that's really not something I would talk about in a standard course.
So there's no r to the -1?
I don't know. Has somebody talked about negative dimension somewhere? Yeah, probably.
Okay.
You talked about rational dimensions, so you can have half the dimension.
There are these things, it's called fractional calculus. It's
I'm confused already.
off the beaten track considerably. I have a book if you want to look at it.
Just focus on this first.
Focus on this course? Yeah, that's probably a good idea. Okay, so anyway, this is kind of low-hanging fruit. Low-hanging fruit, the proof of this isn't that hard. To prove that the dimension of the subspace is smaller than the dimension of the space, if W is not equal to 0, if you have a finite subset of W, you can apply proposition, oh man. Oh, I did just say that, I'm sorry. Did I already do 6.6.5 or did I just scan over by accident? No, I didn't.
You just said 6.5.
Or 6.6.5 said that, if I didn't have enough vectors, if I don't have n vectors in the thing, it won't span it, right? But what could you do? You could just take something outside the span and adjoin it to the set, right? I don't think that's this, that's actually this, I think, really,
You did.
I'm annoyed. I feel like this actually should come after that.
Yes.
So, like I said, there may be some illogic in this section in terms of the structure. I mean, it is true that proposition 6.6.5 can be used to justify that, but actually proposition 6.6.5, which is the one before that we just said that more than n vectors was linearly independent and less than n vectors was not going to span, that proposition actually goes to prove the 6.6.7, which more naturally proves 666. Oh, sorry. I shouldn't say this.
I was like, this is the devil's proposition.
This is the devil's proposition. Yeah,
It's okay, the decimals take care of it.
The decimals take care of it.
The number is 666, not 6.6.6. So we're good. Just always keep the decimals. If you ever erase the decimals.
It's actually 667. Or no, is it? Is it 666 repeating, or is it,
No, it's 6.6 and then 0.6 of the one of the, I don't even know what
It's
you would do if you had
almost
another
90
business.
I'm going now. So,
Sorry.
it's okay. Let V be a vector space, and suppose S is a non-empty set of vectors in V. Then, if S is linearly independent, all right, then there has to exist a vector outside the span, all right? And the union of S with that is linearly independent. Yeah.
Is it supposed to say that if S is linearly dependent?
No, that's supposed to say linearly independent.
Okay. So it's just saying that you can add another vector and it will still be linearly independent. Like a certain vector.
Well, I guess I think there's a word missing here. If S is a linearly independent vector, and maybe, I think this is actually kind of important, and there exists, that's kind of important right here, there should be an and there exists. I think I thought it, but I didn't write it, kind of bad. Because if this set S is a basis, this is an empty gesture, right? If S is a basis, it spans V. There is no such vector V outside the span. However, if the span of S is not equal to V, that means that there exists a vector outside it. And what this says is that S union that vector is linearly independent. This gives us a method to create larger linear independent sets from a given linearly independent set. What you do is you pick something outside the span, tack it on. If possible. If it's not possible, that means you're done. You got a basis. If V is a linear combination of other vectors, then you can remove V from the generating set, and you'll still generate the same. So I mentioned this in a previous class. So. That essentially follows from the fact that linear combinations of linear combinations are, again, linear combinations, yeah. As you can see, the gory proofs are here. Yes, Dr. Professor Landon.
So basically that whole thing with like the, removing the V and like the vector V and adding it, it's kind of like the same thing with the extending and restricted functions. I mean like not many, to make things to make them functions. It's kind of
That's
like the same
not-
principle.
Not a wrong comment. In some sense, it's tied to the question of how do you modify a function to make it injective or surjective. Yeah. I would say that injectivity is kind of like linear independence. I would say that surjectivity is pretty closely tied to spanning. And I also would say that the vector space being finite dimensional, in some sense, is analogous to having a set which is finitely many things in it. Right? A vector space is finite dimensional does not mean that it has finitely many vectors in it, right? The reals have dimension 1. How many real numbers are there? Right. R2 has dimension 2. How many vectors are there in the plane? Infinitely many, right? But the fact that the dimension is 2 means that if you give me 2 vectors, I can build anything else in the plane from those 2 vectors through prescribed things, linear combinations. Proposition 6.6.8, let V be an n-dimensional vector space. Let A, a set S with n vectors, is a basis, all right? If and only if it's either linearly independent, okay, or the span is equal to V. So notice the context here. Context, given an n-dimensional vector space, all right? Step 2, you give me a set with n vectors in it. So the number of vectors matches this number, the dimension of the vector space in which we're asking the question. Then, if the thing spans, that's enough. In other words, I don't even have to check linear independence. If it spans and there's n things in an n-dimensional vector space, game over. So if I give you 3 vectors in R3, for example, and I tell you the span of those 3 vectors is R3, you don't also need to go check and see if they're linearly independent. We already know from the structure of the dimension theory, this proposition in particular, those have to be linear independent. There's no question about it. On the flip side, you give me 4 vectors, all right, in R4, and suppose those 4 vectors are linearly independent. It then automatically follows that the span of those 4 vectors hits all of R4. I don't have to check both conditions for the basis if I'm in the right context. What's the right context? A vector space of known dimension dealing with a set with as many vectors as that dimension. All right? Now, the things I just claimed to you about R3 and R4 are easily verified from what we learned before about column correspondence property and specific calculations on column vectors, but I'm saying something much more general here. So there's that. That's a lovely theorem. Saves you a lot of work. Yes,
So
sir.
basically, if you have like R10 and you have a set with 10 vectors that are linearly, and then you prove are linearly independent, then that would also span R10. I mean, that's kind of like
If what?
If you have like R10 and you have a set containing 10 vectors that you prove are linearly independent, in order to prove it, then that spans R10.
Yes.
Do you have to prove that those 10 vectors are linear independent?
Not if you prove that their span covers all of R10.
Or could you prove they're linearly independent, prove that their span covers all?
Yes. It's
So like,
either.
Yes. But it's not.
Right. Again, with proper context, you need to know that your vector space has 10 dimensions to make these, these collapsing. Another theorem. I got 2 more theorems to go, then I'll shut up for today, guys. S be a subset of finite dimension vector space V. If the span of S is V, all right, but S is not a basis, that means then you can modify S to make it a basis by simply removing redundant vectors. Maybe 20 minutes ago, I wasn't allowing us the flexibility of removing vectors from the set. Now I'm saying if you have a linearly dependent set, you can remove vectors from it until it becomes linearly independent. Now I am assuming we're having a finite set, right? I don't want to try to talk about having an infinite set of vectors and removing infinitely many. That hurts my head. So let's talk about a finite set, okay? But if you have 20 vectors, you're in a 5-dimensional space, you can somehow remove 15 of those vectors and get yourself down to a basis for that 5-dimensional space. If S is linearly independent, but you don't get the whole vector space, then you can modify S to make it into a basis by unioning vectors outside the span of S. Right. These are really useful theorems because this gives you guidance to how to solve problems I will tell you before too long, okay?
What I was talking about earlier was when it was a basis, you can move them. My bad, sorry.
It's okay.
It's yeah. I remember now.
Finally, if V is a finite dimensional vector space and W is a subspace of V, then the dimension W is like, I think I said this already. I think the first sentence in this was earlier in this section. Like I told you, this section could be improved. I'm sorry, you guys, but if the dimension of V is equal to the dimension of W, then V is equal to W. In other words, if you have a 5-dimensional subspace of a 5-dimensional space, it's the whole space. I can't have a 3-dimensional subspace of R3, for example, which isn't just all of R3. I can't have a 16-dimensional subspace of 4x4 matrices unless it's the whole set of 4x4 matrices, and so forth and so on. So next time, guys, I will start into this, and we're going to return to the question of how to solve systems. I'm going to talk about homogeneous and particular solutions to linear systems. This has a lot of bearing on differential equations. Essentially, we're going to discover the particular homogeneous solution set idea, but it's nothing more than an application of the dimension theorem we just went over. So we're going to tie together the reduced echelon form of the dimension theorem. Yes, sir.
Like R2 is like a subspace of R3 and like, and all this stuff.
Well, I don't know what you mean by that. R2 and R3 are objects of different type.
But it has one less dimension of R3, so that like R2 is like.
Can I find 2-dimensional subspaces in R3?
Yes.
Absolutely. Yeah. I'm just being picky. I mean, it is.
R2 is